Now let us see the electric field due to conducting spherical shell and uniformly charged sphere. Now we have to know what is the difference between these two. Spherical shell, that means the charges are distributed on the surface of the shell. Okay, inside this shell we don't have any charge. That is what we mean by conducting. If this is a conducting surface, then the charges will be present only on the surface. No charge is present inside. If you take uniformly charged sphere, the charge is uniformly distributed all over its volume. So this is the difference between conducting spherical shell and uniformly charged sphere. So now let us see what are the electric field at a point inside the surface, I mean inside the shell, and on the surface, and at a point outside the shell. We will see these three cases. If you take inside some point inside in the shell, conducting shell, inside the sphere we don't have any charges. So if there are no charges inside, then the electric field inside will be 0. So the internal point, the electric field is 0 for conducting shell. Okay, conducting spherical shell. Now I have shown phi E equals to EA, and that is equals to Q enclosed by epsilon naught. So Q enclosed is 0, so it is 0 only. Okay, now let us consider point outside. So for the point outside, so we are going to assume the Gaussian surface. We know phi E equals to integral integral E dot dA, that is electric field and areas dot product. So we assume, suppose if this is the conducting shell, then our R is somewhere outside. This is the point where we have that R, that is the distance between the center to this point is small r. Okay, capital R is radius and small r is the distance which we want. So this is the distance. Okay, that is small r. Then we assume a Gaussian surface like this, a sphere with a radius of small r. Okay, then what is the area of that sphere? That is 4 pi small r square. Then what is phi? It is cube by epsilon naught, that is equals to E into 4 pi r square. So what is the charges? This is the charge. If suppose the charge is q, then we have to take that q. From this, E equals to 1 by 4 pi r square q by epsilon naught. So how can we write this? 1 by 4 pi epsilon naught is k. So we are writing k separately, q by r square. So this is the general formula for finding electric field at a point which is at a certain distance small r from the center of the shell. Okay, now let us see what is the point if it is at surface. So at the surface, small r, that is this distance, so this I have told small r. So if it is at the surface, this is the point, then small r is equals to capital R. So instead of this small r, you have to substitute the capital R. So E equals to kq by capital R square. So this is what is the electric field at the surface in case of a conducting spherical shell. Now we will see all the cases for uniformly charged sphere. So this is the uniformly charged sphere. So the charges are distributed all through its volume, and we have a point at certain distance, that is small r, from the center of the sphere, and the radius of the sphere is capital R. Okay, now for the internal point, so please see here in the internal points, all the inner surfaces, there is charge. So if there are charges, then there will be electric field. So electric field is not 0 inside. So electric field has some value inside the uniformly charged sphere. So please note that difference. So internal point, the electric field at internal point, that is kqr by r cube. So what is this small r? So if suppose this is the sphere, and if suppose this is the center of the sphere, and if suppose this is the point where we have to find the electric field, and that distance is r from the center. Okay, so here r is nothing but a point inside the surface. Okay, or I can say r is less than capital R, small r is less than capital R. Okay, if that is the case, then how do we find the electric field? That is kq small r by r cube. So this we are just seeing the conclusion. Okay, yes, if we take at the center, so if this is the center point, then in the center point the distance smaller is 0. Okay, if the point is itself at the center, then the small r, value of small r is 0. So electric field at the center will be 0. So please note that. Now we will see for the point outside. So for the point outside and at the surface, so the case is similar to that of conducting spherical shell. Okay, there is no change in the formula, or there is no change in the method of finding them. So it is same as that of like that. So for the outside, it is E equals to KQ by small r square. That is the distance of the point from the center of the sphere. And at the surface, small r will be equals to capital R. So E equals to KQ by capital R square. Now we will see the graphical representation for electric field. So here we have conducting sphere, that is a shell, okay, where the conducting means the charges will be distributed over the surface. Next we have uniformly charged sphere, where the charges are uniformly distributed entirely in its volume. Now let us see the graphical way of representing. So we know if it is a conducting sphere, the inside every point we have electric field 0. So up till R, okay, the graph, it is in this axis we have represented the distance, and in this axis we have represented the electric field. So up till R, up till the radius, there is no electric field, there is no value of electric field. So if you take at the surface, that is exactly at R, then the electric field is maximum, that is KQ by capital R square. Okay. Yes, KQ by capital R square. Then after that, it is the formula is KQ by small r square. So from this, what I can write, electric field is inversely proportional to r square. So the graph is like that. Okay. Now let us see for the case of uniformly charged sphere. So here, yes, we have seen the formula for up to, that is the internal points. What is the formula we have seen? KQR by r cube. So that is electric field is directly proportional to small r, or electric field is proportional to the distance from distance of the point from the center. So that is what we have shown. So E is directly proportional to r. So up to the surface, the graph is a straight line because E is directly proportional to r. So at the surface, we know it is the maximum value, that is same as that of like the shell, that is KQ by r square, capital R square. Then after that, it is inversely proportional to small r square, that is KQ by r square, the same one. So the graph is like this. Okay, so this is all about conducting sphere and uniformly charged sphere. So we can see for points outside the charged spherical shell, the shell behaves as if all the charges are concentrated in its center. Okay, so here the charges are at the surface, but for the point outside, we see the formula is KQ by r square. So in such a case, we can see the shell is behaving as if all the charges on the surface are at the center, or concentrated at the center. So uh, we can say it behaves like that. Let's just see the questions. The first question, 2-point charges plus E and minus E are kept inside a large metallic cube without touching its sides. Electric flux emerging out of the cube is. So inside a very big cube, we have placed two charges, one is plus E and one is minus E. So what is the flux through that? So we know phi is equals to Q enclosed by epsilon naught. So what is the Q enclosed plus E minus E? So it is 0. So that is the answer for the question. Number 2. A short electric dipole consists of 2-point charges plus Q and minus Q is placed at the center of center O inside a large cube of length L. Electric flux emanating through cube is. So here also the same case, but here it is a dipole. So the dipole means it is a consisting 1 plus Q and minus Q separated by a short distance. So that is what is electric dipole. So again the same reason, it will be plus Q minus Q by epsilon naught. So the answer is 0. So here also the flux is 0. Let us see this question. A rectangular frame of area 10 meters square is placed in a uniform electric field of 20 Newton per coulomb with normal drawn on the surface, making 60-degree angle with the direction of electric field. What is the electric flux through the frame? So they have given the normal drawn on the surface. The normal drawn on the surface means it is the area vector. Okay, that area vector is making an angle 60 degree with the direction of electric field. So if suppose this is the electric field and this is the vector area, then the angle between these two is 60 degree. That is what is given in the question, and they are asking us what is the yes, flux is asked. So phi is equals to E dot A. So that is nothing but EA cos theta. What is cos theta? That is theta. What is theta? It is the angle between electric field and the vector, area vector. So it is 20. That is area is 20. Sorry, electric field is 20 Newton per Coulomb. Area is 10 meters square, and cos theta is cos 60. So 20 into 10 into 1 by 2 is equals to 100 volt per meter. Sorry, 100 volt meter. So that is the answer for flux. Let us see this question. A closed surface has n electric dipoles located inside it. Flux through the surface. So, if there is one dipole or if there is n number of dipoles, one positive charge will be there, one minus charge, a negative charge will be there. So the net charge inside the closed surface will be 0 only. So there is no flux. So the answer is 0. Let us see this question. The nucleus of hydrogen atom is a sphere of radius 10 power minus 15 meter. The electric field at the surface of the nucleus is. So, we have to assume the nucleus of hydrogen atom is a sphere and with, whose radius is 10 power minus 15 meter. Now we are asked to find the electric field at the surface of the nucleus. So the general formula is E equals to kq by r square. We have just now seen that. And here small r is nothing but capital R. Okay, because it is at the surface. What is the value of K? It is 9 into 10 power 9. What is the value of Q? So if you take hydrogen, nucleus of hydrogen atom, then there is only one proton. So what is the charge on one proton? That is 1.6 into 10 power minus 19 coulomb. So that is the charge we have to take. What about R square? It is 10 power minus 15 into 10 power minus 15. So what is the answer we get? It is 14.4 into 10 power 20 volt per meter. So that is the value of electric field at the surface of the nucleus. So this is electric field. Okay, let us see this question. A closed surface in vacuum encloses plus q and minus 3q. What is the total electric force emerging out of the surface? So yes, we have to just add the charges. So it is minus q, sorry, it is actually minus q and plus 3q. Okay, please note this, minus q plus 3q. So simple addition will give us 2q by epsilon naught. That is what is phi enclosed is 1 by epsilon naught times the charge enclosed. So it is 2q by epsilon naught. That is the answer. Electric field intensity E at a point P at a perpendicular distance small r from the infinitely long linear charge xx having linear charge density lambda is given by. So this is a simple question which the formula is the direct answer. So this is the infinite wire they are asking us to assume, and this is the point P which is at a distance, the distance, or is it perpendicular distance is r from the wire. Okay, then what is the electric field at the point P because of this infinite charge? So it's 2k lambda by d. So what is that? 2, and what is k? It is 1 by 4 by epsilon naught lambda by what is the distance we have to take? Here it is small r. So we are taking small r. So that is the answer.